What is the actual limit of physics when it comes to building a casting machine? That is the exact question Elon Musk asked his engineering team, and the answer they came back with is honestly hard to believe. Right now, at Tesla's Texas Gigafactory, around 1,000 welding robots are on their way out. In their place, Tesla is setting up a production line built to finish an entire vehicle in under 30 seconds, powered by a machine capable of applying up to 50,000 tons of clamping force. It sounds like science fiction, but this is the real plan Elon Musk is using to try to bring Tesla back to what many call its golden age, and it all revolves around one machine designed to bend the rules of manufacturing physics. To pull this off, Tesla has unveiled the fourth generation of its Giga Press, built specifically to produce the company's most advanced vehicles yet. With up to 50,000 tons of clamping force and a footprint about the size of an actual house, this machine could theoretically produce a full vehicle structure at a speed that almost feels impossible. So what exactly is Musk planning here, and how could a single machine end up shaking the entire automotive industry? Let's break it down. The story really starts with that one question Musk kept asking his team: how big can a casting machine actually get before physics says no more? It was never just a slogan. Tesla has spent years turning that question into a genuine engineering challenge. The earliest Giga Press machines let Tesla take dozens of small parts that used to be welded together and replace them with a single, massive aluminum casting instead. 6,000 tons of clamping force was enough to transform how the Model Y got built. 9,000 tons pushed that even further. But jumping all the way up to 50,000 tons is a completely different story. This isn't just about making a bigger machine anymore. It is an attempt to find out whether the entire philosophy behind building a car body can be reinvented from the ground up. So why does Tesla actually need 50,000 tons of clamping force? To understand that number, we need to understand what it really represents. The Giga Press doesn't use 50,000 tons of force to simply squash aluminum into a mold like some giant hydraulic press. That figure refers to clamping force, which is the force needed to keep the two enormous halves of the mold locked tightly together while molten aluminum gets injected inside at extremely high pressure. That injected metal creates a force that constantly tries to push the mold halves apart. The bigger the mold and the higher the pressure, the more clamping force you need to keep everything sealed. If that force isn't enough, the mold can actually separate mid-cycle, ruining the entire casting and potentially letting molten metal escape. This is where 50,000 tons becomes genuinely intimidating, because Tesla isn't just trying to build a bigger part. It wants to build it dramatically faster too. According to Musk, the real goal is to push manufacturing speed closer to something you'd see on an electronics assembly line, with each casting cycle reportedly taking around 5 seconds and multiple components produced within that same cycle. But hitting that kind of speed means Tesla can't just crank up the clamping force and hope the rest works itself out. Every part of the process has to be synchronized down to the second. It all begins with the aluminum itself. Fresh material, along with recycled aluminum from earlier casting cycles, gets fed into a furnace and heated to roughly 850 degrees Celsius until it turns fully molten. Once surface impurities are skimmed off, that molten aluminum moves into a sealed holding furnace where the temperature stays locked in the correct range, keeping the metal ready for the next injection at all times. Reports describe a two-furnace setup, one for melting and one purely for holding the metal at a stable temperature before it's injected. Even here, Tesla has to deal with a problem you can't see with the naked eye. Molten aluminum reacts with its surroundings and can trap gases or pick up unwanted particles. That's why the system relies on a controlled gas environment, argon degassing, and silicon carbide filters to strip out larger impurities. Only once the metal hits the required purity level does it move on to the most critical stage of the entire process, the casting mold itself. Before each cycle, the mold gets coated with an extremely thin lubricant layer so the finished part can be removed cleanly afterward. The system then pulls a vacuum inside the mold to eliminate trapped air, which matters enormously when you're producing a massive structural part at extreme speed, since even a tiny pocket of trapped gas can ruin the quality of the final piece. Once everything is set, a high-speed piston forces the molten aluminum into the mold cavity with enormous power, and from that point on, everything happens in a matter of seconds. The hardest part of all this is staying fast without losing precision. Inject the metal too quickly and you risk trapped air or flow defects weakening the internal structure. Inject it too slowly and the aluminum starts cooling before the mold is even fully filled. With a component this massive, one small section that doesn't fill properly can turn the entire part into scrap. Tesla has described this as a genuinely delicate engineering balancing act, where the metal has to cool exactly right while every step after casting gets automated to turn that glowing hot part into something usable. That's exactly why the cooling system matters just as much as the clamping force. When the freshly cast piece comes out of the mold, it can still be sitting around 400 degrees Celsius. It then runs through a cooling system to bring that temperature down fast, while the mold itself gets cleaned and cooled to prep for the very next cycle. Reportedly, this entire sequence is timed so precisely that a new casting cycle can start just 1 to 2 minutes after the previous one wraps up. Any excess aluminum gets trimmed and recycled straight back into the melting process to cut down on waste, and the finished component finally goes through X-ray inspection to catch any internal defects that would otherwise stay completely invisible. Now you might be wondering why Tesla is going through all this trouble just to produce one giant part. It's because every component you eliminate from a car also eliminates an entire chain of manufacturing work behind it. That's really the whole point of the Giga Press. A traditional vehicle is built from hundreds of separate components joined together with welding, bolts, rivets, and adhesives. Every single joint is another manufacturing step, every step needs its own equipment, and every piece of equipment needs factory space, maintenance, and quality checks. Tesla is trying to flip that entire equation by turning dozens of small parts into one large integrated structure. Reports suggest Tesla is targeting somewhere around 80 major structural components for the Cybercab, compared to roughly 200 for the Model Y. If that number holds up once production actually starts, it would mark a genuinely major shift in how vehicles get engineered. Think about it this way, if one component can replace dozens of smaller parts, Tesla isn't just saving assembly time. It's also cutting out welds that could become weak points down the line, reducing mechanical connections, and creating a more continuous structural design overall. There's a common misconception worth addressing here too. People often assume that if a structure is made of 70 welded pieces, you can just swap out whichever single piece gets damaged. But once those 70 pieces become one massive aluminum casting, a crack in even one small area could mean replacing the whole casting. On paper that sounds like a real downside, but in practice, repairability really comes down to how the manufacturer engineers the crash zones and repair procedures around that casting, not simply how many pieces make up the structure. Tesla actually provides dedicated repair procedures for the Model Y's rear mega casting. In plenty of cases, technicians can cold straighten bent sections, weld small cracks, add reinforcement plates, or even replace individual rail sections instead of swapping the entire casting. Only when damage hits critical areas or crosses certain limits does the whole assembly need replacing. Back in 2025, Thatcham Research, a UK-based group focused on automotive repair and risk analysis, published findings from 2 years of crash testing and repair work done directly on the Model Y. Their conclusion was that the mega casting wasn't just reparable, it could actually be cheaper to fix than a traditional multi-piece steel structure. Compared to the Model 3's conventional rear structure, repairing a damaged Model Y casting came out roughly $2,800 cheaper, and even a full casting replacement was still around $675 cheaper. So the fear that one crack means throwing away the whole car never really held up. What actually matters is how well Tesla designs that casting to be repaired in the first place, and real-world crash testing on the Model Y has shown the opposite of that original concern. Tesla's whole strategy here is to automate fewer individual steps while making each remaining step capable of doing far more work. Instead of hundreds of robots assembling countless small pieces, one Giga Press performs a single operation that produces an entire massive structural component. That's the real difference between simply automating an old factory and completely redesigning it, so many of those old manufacturing steps disappear altogether. And if this 50,000-ton target actually becomes reality in mass production, the competition among automakers won't just be about who owns the biggest casting machine anymore. It'll be about who can design a vehicle truly built to take full advantage of a machine this massive, because you can't just take a car designed for traditional manufacturing and drop it into a Giga Press. Engineers have to rethink the shape of every structural component, how forces move through it, how it cools, how it comes out of the mold, where every connection point sits, and how it all integrates with the rest of the vehicle. That's likely why the Cyber Cab is expected to be the very first product to use this next-generation Giga Press. Musk has said the 50,000-ton machine could potentially cast 5 vehicle bodies in a single cycle, which backs up his claim that the Cyber Cab could become the fastest mass-produced vehicle ever built, with volumes potentially exceeding the Model 3 and Model Y combined. So how exactly does a smaller car like the Cyber Cab fit into a much bigger machine? At first it seems backwards. The Cyber Cab is smaller than the Model Y, yet Tesla wants an even larger press to build it. The answer is that Tesla doesn't need this giant machine to build a bigger car, it needs it to cast more of the vehicle in a single cycle. With the roughly 6,000-ton press currently used for the Model Y, Tesla already turns the rear body into one large structural casting, replacing dozens of small parts and hundreds of welds, and applies a similar approach to the front body too. But right now those two sections are still cast separately, which means the body still needs extra steps to join them together. The 50,000-ton Giga Press aims to take this idea much further. Instead of casting the front and rear separately, Tesla wants to produce the entire Cyber Cab body structure in one single casting cycle. That's exactly why the clamping force needs to jump so dramatically, even for a smaller vehicle. As the size of a single casting grows, so does the mold surface area, the amount of molten aluminum required, and the forces trying to pull that mold apart. So this 50,000-ton figure was never really about building a bigger car. It's about packing more manufacturing steps into a single cycle. If Tesla pulls this off, it could keep eliminating robots, joints, and entire assembly operations while slashing production time even further. And that brings us right back to Musk's original question about the true physical limit of a casting machine. He isn't just trying to find out how big one machine can get. He's trying to find out how much of an entire vehicle a single casting can actually produce. There's an even more radical idea Tesla is exploring for the Cyber Cab too, integrating color directly into the material of the body panels instead of producing bare metal panels and running them through a multi-layer paint process. If that technology actually works at scale, Tesla wouldn't just have a faster Giga Press, it could start eliminating one of the largest, most energy-hungry parts of the entire factory, the paint shop itself. That's a story for another episode, so make sure you're subscribed so you don't miss it. So what do you think about the way Tesla is trying to completely reinvent vehicle manufacturing? Drop your thoughts in the comments below, hit that subscribe button here on Drive Tech Tesla for more breaking Tesla updates, and I'll see you in the next one.